Hello, today I'm going to have a look at a technique called integration by recognition. You might also know it as integration by inspection. And how it works is we're going to have a look at different equations which we can differentiate, and then because we know that integration is the opposite of differentiation, we can work out how our answers integrate back to the original equation. All of these come from using the chain rule. Now, there are going to be videos on using the chain rule, so have a look at those for a slower approach. I'm going to do the shortcut. So rather than making a substitution, I'm just going to do it all in one go. And we're having a look at these particular equations. So we've got y equals k f of x to the power n, y equals k e to the f of x, and y equals k ln of f of x. So the first one, I'm going to pretend that rather than f of x, it's just x. When I differentiate kx to the n, I get k times n, x to the power n minus 1. But it wasn't really an x, it was f of x. So I'm going to put f of x here instead. And then I need to multiply that by what I get when I differentiate f of x, which is f dash x. So I know that this ends up being k times n, f of x to the power n minus 1 times f dash x. The important thing to notice here is that k and n in this case are both constants. So we have a constant times f dash of x times f of x to a power. So this is going to be the key thing we're looking for, a constant times a derivative times the original function to a power. The next one we're going to have a look at is y equals k e to the power f of x. So again, I'm going to differentiate this by pretending that rather than f of x, it's just x. When I do that, I know that I'm going to get k e to the power x. But it wasn't really x, it was f of x. So rather than x, I'm going to write f of x. And using the chain rule, I need to multiply by what I get when I differentiate my f of x, which is f dash x. So in this case, what I get when I differentiate is a constant times my derivative times e to the power of my original function. The last one we're going to have a look at is y equals k ln of f of x. So again, when I differentiate this, I'm going to pretend that it's an x. So that gives me k times 1 over x, or k over x. But it wasn't really an x, it was an f of x. And using the chain rule, I know that I need to differentiate what's inside my bracket, so that's going to give me f dash of x. I can rewrite this as my constant times f dash of x over f of x. So these are the three things which we're looking to spot. We're looking to spot f dash of x times f of x to a power. We're looking for f dash of x times e to the power f of x. And we're looking for f dash of x over f of x. And these can all be out by a constant. We've got k in front of all of them. So let's have a look at how this helps us with our integration. So let's have a look at a question. The question is, I want to integrate 4x minus 2 times x squared minus x plus 7. The first thing that we need to do is we need to spot that if I differentiate x squared minus x plus 7, I get 2x minus 1. And that is half of this. So I'm out by a constant, which is what we're after. If this is differentiated to 2x minus 2, there isn't a constant I could multiply by to get 4x minus 2, and then I'd have to do another method to integrate it. But because this is out by a constant, I can use my integration by recognition. If we flick back to the previous page, now if you remember, when we differentiated y equals k f of x to the n, we ended up with n minus 1 as my power. So what I'm going to do is I'm going to add 1 to my power. So I'm going to have a bit of a think in a thought bubble about what happens if I differentiate x squared minus x plus 7. And instead of doing that to the power 5, I'm going to add 1 to my power to do it to the power 6. When I differentiate this, well, I'm going to get my x squared minus x plus 7, And then I'm going to take 1 off the power times by the original power. But then using the chain rule, I've got to differentiate the part inside my bracket, which gives me 2x minus 1. So at the moment, I'm getting 6 times 2x minus 1 times x squared minus x plus 7 to the power 5. I actually want 2 times my 2x minus 1. So what I'm going to do is I'm going to put a third in my original function. And now when I differentiate, that's going to carry on through. So that will give me the 2 that I want at the start. So integration by recognition is really just having a bit of a try, seeing what happens when you differentiate. We should probably write d by dx equals. And because when I differentiate this function, I get what I want, I know that when I integrate this, I'm going to end up with this. So I can say my 4x minus 2 times x squared minus x plus 7 to the power 5 integrates to, and it's the third x squared minus x plus 7 to the power 6. So I'm just writing out what I did here. When it comes to trig functions, it's often a lot harder to spot integration by recognition. Here's a classic one, integrating sine cubed dx. And what we need to do for this is we need to write it as sine x times sine squared x. And then I can use our core 2 knowledge to change sine squared x into 1 minus cos squared x. And then I can expand that to give me the integral of sine x minus sine x cos squared x dx. Well, we know how to integrate sine x. We know that sine x integrates to minus cos x. What we need to have a look at is integrating our minus sine x cos squared x. Cos x I know differentiates to sine x. So here we have our f dash x times our f of x to a power. Just like before, I'm going to, in a bit of a thought bubble, I'm going to add 1 to my power. So I'm going to say we have cos cubed x, and when I differentiate that, so I'm going to say d by dx to say the derivative is equal to, when I differentiate this, I times by the power, and then I take 1 off the power, but then I need to use the chain rule. So I'm going to differentiate my cos x, and I get minus sine x. So this is equal to minus 3 cos squared x sine x. But I didn't want minus 3 cos squared x sine x. I wanted minus 1 cos squared x sine x. So to get rid of the minus 3, I'm going to start with a third in my original function. That will just carry through, and that will give me my minus 1. So I know that this is what I wanted. This is what I had to differentiate to get it. So I can say now that when I integrate sine x cubed, I'm going to get my sine x integrates to minus cos x, and the minus sine x cos squared x becomes a third cos cubed x. And obviously we need our plus c at the end. Let's have a look at the next sort. So we want to integrate our 30x to the power 4 plus 18 times e to the power x to the power 5 plus 3x. Well, the key thing here is to spot that if I differentiate this, I'm going to get x to the power 4 times 5 plus 3. And if I times this by 6, I get the bracket here. So this is the form e to the power f of x times f dash of x. And what I'm going to try doing is, if we look back at our differentiation, what we started with ended up being the same as what we had without the f dash x bit at the start. So let's try that. In my thought bubble, I'm going to say, what happens if I start with e to the power x to the power 5 plus 3x minus 2, and I'll try differentiating that. Well, when I differentiate that, I'm going to get e to the power x to the power 5 plus 3x minus 2. And using the chain rule, I know that I now need to times by what I get when I differentiate this bit, which is going to give me 5x to the power 4 plus 3. Well, that's almost what I want, but it's not quite what I want. So what I'm going to do is I'm going to add in a times 6, because a times 6 here will give me a times 6 here, and now this is what I want. So I can now say, because I know what I need to differentiate to get what I want, when I integrate what I started with, I'm going to get the integral of 30x to the power 4 plus 18 times e to the power x, this nice polynomial, is equal to 6 lots of 5x to the power 4 plus 3 e to the power x to the power 5 plus 3x minus 2 plus c, because it would be really silly to forget the plus c. For the second example, we're going to have a look at 3 sec squared x times e to the tan x. So when I differentiate tan x, we know that we get sec squared x. So this is exactly what we're looking for. I'm out by a constant, so I can use integration by recognition. Just like usual, I'm going to do a thought bubble, and I'm going to say, what happens if I do e to the tan x? When I differentiate this, I'm going to get sec squared x e to the tan x. So I got that by differentiating. Now, we've got one lot of sec squared x e to the tan x. We wanted 3 lots of sec squared x e to the tan x, so I'm going to put a 3 here. To get that 3 there, I needed a 3 in my original. So I can now say, outside my thought bubble, the integral of 3 sec squared x e to the tan x is equal to 3 e to the tan x plus c. And finally, let's have a look at our fractional ones. So if I wanted to integrate 6x squared minus 8 over x cubed minus 4x, well, the hardest bit is thinking about integration by recognition and spotting that when I differentiate this, I'm going to get 3x squared minus 4, and to get the bit on the top, I just need to times by 2. So we can see straight away that this is a case of my f of x. On the bottom of my fraction, I've got f dash x on the top of my fraction, and I've multiplying by a constant. So going back to our first slide, we have this situation here, our third situation. So I know that to begin with, I need ln of f of x. So in my thought bubble, I'm going to say, what happens if I start by doing the natural log of x cubed minus 4x? Well, when I differentiate that, I'm going to get 1 over x cubed minus 4x times by what I get when I differentiate x cubed minus 4x, which is 3x squared minus 4. I don't want just this, I want 6x squared minus 8 on the top, so I need to times by 2. To get that times 2 in my answer, I need a times 2 in my question. And now I can say I know what will differentiate to give me the question. So because differentiation and integration are opposites, I can now say that the integral of 6x squared minus 8 over x cubed minus 4x is equal to, and then it's just what we had in our adjusted thought bubble. So 2 log x cubed minus 4x. Again, the trig ones can be hard to spot. The classic one in this case is tan x. Now this is in the formula book, but you can be expected to show it, so you do have to learn this. The integral of tan x, well, we know that tan x is sine x over cos x, and if I integrate And if I differentiate cos x, I get minus sine x. So I get minus sine x over cos x times minus 1. I'm out by a constant. You can see my f dash of x over my f of x and my constant. So just as we've been doing for all the rest of the integration by recognitions, bit of a thought bubble. What happens when I differentiate the natural log of my f of x, so cos x? Well, when I differentiate that, I'm going to get 1 over cos x multiplied by what I get when I differentiate cos x, which is minus sine x, which is almost what I want, except I want to times that by minus 1, so I'm going to stick a minus at the start, and I can now say that the integral of tan x is equal to, dx, is equal to minus log of cos x plus c. Now, the observant ones among you will have spotted that that's not what's in the formula book, but I can use my laws of logs to bring my minus to be a power, which gives me 1 over cos x, and we know that 1 over cos x is sec x, so this is log of sec x plus c. And that is what it says in the formula book. So you can see just how useful this is. Let's recap the 3 which we've looked at. So we know that if I've got to integrate something which looks like k f dash of x, f of x to a power, I'm going to try and see what happens when I differentiate f of x to the power n plus 1. If I'm asked to integrate f dash of x e to the x times a constant, what I'm going to do is I'm going to try and see what happens when I differentiate e to the f of x. And the last one which we need is if I'm asked to integrate k times f dash of x over f of x, I'm going to see what happens when I try differentiating the natural log of my function of x. Right, I know it's been a long video. If you stick with me a little bit longer, we'll just have a look at how this crops up in exam questions. Now, this first one says to use the substitution, and in the exam you would have to use the substitution. If it says to do it by substitution, you must do it by substitution. I can't find any trig questions which are like this, so this one, I'm taking this one. It has come up in other exam boards, and it is perfectly possible that it could come up in OCR. So let's have a go at this. I'm going to do it by recognition, as I say. So what I'm going to do is I'm going to change it so that we get sine x, sine squared x, cos squared x. And then, just like we did in the example earlier, I'm going to change my sine squared x to 1 minus cos squared x. And I still have my cos squared x dx. So you can see I've got my sine x is my sine x, my 1 minus cos squared x is my sine squared x, and my cos squared x is still my cos squared x. And all I'm going to do is I'm going to expand my brackets. So that will give me sine x cos squared x minus sine x cos to the power 4x. So now I have 2 recognition questions to have a go at. So for the first one, I'm going to try adding 1 to my power, so I'm going to see what happens with cos cubed x. When I differentiate that, I'm going to get 3 cos squared x times by what I get when I differentiate cos x. When I differentiate cos x, I get minus sine x. So that gives me minus 3 cos squared x sine x, but we only want 1 sine x. So to change my minus 3 to a 1, I need to times by a third. So I'm going to times by a third at the start. For the second part, I'm going to try. Now this is cos to the power 4x. I'm going to add 1 to the power, so I'm going to try cos to the power 5x. When I differentiate cos to the power 5x, I'm going to get 5 cos to the power 4x times by, and when I differentiate cos x, I get minus sine x. So this is minus 5, and I only want minus 1. So I'm going to put in a fifth, which means I need a fifth at the start, and that will carry through my calculus. So I can then say that the integral of what we had before is equal to, and I now know that this first bit is going to give me minus a third cos cubed x. Oh, I've missed out the minus there. So we're going to get minus a third cos cubed x. And then on the second one, I had my minus already, so this is going to come from the differentiating, and I'm just going to write my fifth cos to the power 5x. And then I apply my limits, and that will give me what the answer is. Again, I can do this by recognition. Because it says in the exam question to do it by substitution, in the exam you would have needed to do it by substitution. Here's a second question. This actually shows us that it's a recognition question. It says, part I, state the derivative of e to the power cos x. Because it's state, they're not expecting to see any working out, they're expecting you to just be able to do this straight away. So I can say that the derivative is e to the cos x, because that's not changed, times by what I get when I differentiate cos x, well that's minus sine x. And then part II, here we've got the integral, and the key thing to spot is this section, the sine x e to the power cos x, is similar to what we had previously, but it's out by a constant. So the question is, integrate cos x sine x e to the power cos x dx. Well, this is going to be an integration by parts question, and then just for extra difficulty, we're going to have to do recognition within it. So because I know how to integrate this, I've spotted that this part is an integration by recognition. I'm going to call this part my dv by dx. Because this part is the other part, I'm going to call this u. And then we'll see what happens as we're working through this. So I know that to do my integration by parts, we're going to have to differentiate my u section. When I differentiate cos x, I get minus sine x. When I integrate my sine x e to the power cos x, well, I know that this is my f dash of x times f of x times a constant. So we're going to try and see what happens when I differentiate e to the power cos x. Well, that gives me, as we did previously, sine x e to the power cos x times by minus 1. I want to get rid of this minus, so I'm going to do minus 1 times this. So I'm going to need a minus at the start. So I can say v is equal to minus e to the power cos x. So now I've got my u and I've got my v, I've got my du by dx and I've got my dv by dx. I can use my formula for integration by parts, which is u times v minus the integral of v du by dx. U is cos x, v is minus e to the power cos x, and then we're going to do minus the integral of v, which is minus e to the power cos x multiplied by my du by dx, which is minus sine x. So this is minus cos x e to the power cos x minus the integral of sine x e to the power cos x. Now I can bring this minus sign inside the integral, and this now is exactly what we had in part I. So I know this is going to integrate to e to the power cos x. So I can say that the answer is minus cos x e to the power cos x plus e to the power cos x. Now, because I'm doing this quickly, I've missed out my limits, but we're going to need the limits pi by 2 and 0. Now you should have your limits written on each integral as you're going through, and you should also have them written here like this. I'm not going to finish that question off, but if you substitute in those numbers, you will find that the answer matches up to the mark scheme. And the last question I'm going to do, I know it's been a really long video, just bear with me for one more question. Given that a sine theta plus cos theta plus b cos theta minus sine theta is identical to 4 sine theta, find the values for constants a and b. So not really an integration by recognition question, but it's going to lead on to one. Let's start off by doing the only thing which we really know how to do, by expanding our brackets. So we get a sine theta plus a cos theta plus b cos theta minus b sine theta is identical to 4 sine theta. Now it doesn't matter what value of theta we put in. This will always give me 4 sine theta. So I know that the number of sine thetas must be the same. So I know that my a sine theta and my minus b sine theta must provide me with the 4 sine thetas. Now I know that there are no cos thetas on the right hand side, so I know that my a cos theta and my b cos theta must be equal to 0, so I can say a plus b cos theta is equal to 0. This lets me form two simultaneous equations. I can say a minus b is equal to 4 and a plus b is equal to 0. I'm going to add these equations, so I'm going to say 2a equals 4, a is equal to 2, and therefore b must be equal to minus 2. Alright, so we've found the values of our constants a and b. Now we're asked to integrate this lovely expression, 4 sine theta over sine theta plus cos theta. And we know from a previous section that 4 sine theta is identical to our a sine theta plus cos theta. Well, our a is 2, so it's 2 sine theta plus cos theta. And plus b cos theta minus sine theta. Well, b is minus 2. We're expecting to need to use the previous part. We've got a 4 sine theta here, we've got a 4 sine theta here. So even if I don't know where it's going to lead, I'm going to have a go at replacing it. And I'm going to end up with the integral between pi over 4 and 0 of 2 sine theta cos plus cos theta minus 2 cos theta minus sine theta, all over our sine theta plus cos theta d theta. Now I'm going to do the opposite of subtracting fractions. When I subtract fractions, I make the denominators the same, what I'm going to do is I'm going to split up my fractions to make it two separate fractions. So I'm going to get the integral between pi over 4 and 0 of 2 sine theta plus cos theta over sine theta plus cos theta. And then I'm going to take away 2 lots of cos theta minus sine theta over sine theta plus cos theta. Here I've got the same on the top and bottom being multiplied all the way across my fractions, so I can cancel them. And I'm left with the integral between pi over 4 and 0 of 2 minus 2 cos theta minus sine theta over sine theta plus cos theta. And that doesn't look much better than what we had to begin with, except we know that we're thinking about integration by recognition. And if I try differentiating my sine theta plus cos theta, I'm going to get sine theta differentiates to cos theta, and cos theta differentiates to minus sine theta. So my fraction is my constant 2 times my derivative over my original function. And thinking back to our integration by recognition, I know that means I'm going to have to try seeing what happens when I differentiate the natural log of sine theta plus cos theta. When I differentiate that, I get 1 over sine theta plus cos theta times by what I get when I differentiate that, which is cos theta minus sine theta. And then to get the 2 here, I need to have a 2 here. And to get that 2 there, I'm going to have to multiply my original by 2. So I can now say that the integral of pi over 4 to 0 of 2 minus 2 cos theta minus sine theta over sine theta plus cos theta is equal to, well, when I integrate 2 with respect to theta, I'm going to get 2 theta. And we now know that when I integrate this fraction, I'm going to get my 2 log mod of sine theta plus cos theta. And I'm going to put in my limits. My limits were 0 and pi over 4. So I'm going to get 2 lots of pi over 4 is pi over 2 minus 2 times the natural log of sine theta. Well, pi over 4 is 45 degrees. So sine of 45 degrees is root 2 over 2. Plus cos of 45 degrees, that's also root 2 over 2. So we get pi over 2 minus, and when I add my root 2 over 2 plus root 2 over 2, I get root 2. So I'll get root 2, I'm going to bring the 2 up to be a power, so I'm going to get the natural log of root 2 squared. And the squared is inside the log. So this is pi over 2 minus the natural log of 2. And if I have a look back at the original question, we wanted a times pi minus the natural log of b. And that is exactly what we've got. So that's the end of my video on integration by recognition. Sorry it was so long, but I hope that's been helpful to you.